Welcome to the ninth video in Introduction to Quantum Field Theory. In this video, we'll be talking about gauge and connection. We covered local coordinate systems in the last video. I recommend you watch the last video if you don't remember even a little bit. We're going to cover some of the basics of what was covered in the last video. We'll cover some of that in this video, but we're not going to review everything. So I recommend going back and watching that one because this whole segment revolves around the ideas in that video. So we're going to talk about something. There is an important nuance in the connection A mu from yeah, A mu. So the idea here is that transporting the connection throughout a loop. Okay, I keep writing B's. Loop in space-time doesn't always return A mu to its original state. We have things like this already, so this might seem like a weird idea that you go in a loop and you end up with a different value than what you started with. But we know of plenty of systems like this. So let's first cover an example. So we'll say a loop with the same initial and final points. I'll just write these like this. It's easier to see. So for an example of this is if we have two-dimensional Euclidean space, then we get some kind of box like this. And if we consider some arbitrary loop where you start here, and you just travel along the loop like this, then you're going to get that the initial value, so say a mu at, let's see, some initial, we'll just call it time for now, but it's not necessarily time. Its position and a mu, they are equal. So what would this look like specifically? It would look more like if I have this, if I have a vector like this, then start here, copy. So if I have this vector right here, copy that, and I transport it along. So it looks like this. It's being annoying. And keep transporting it. You can see that it comes back to itself. So the loop can be curved, but the space itself is flat. So the vector as it's transported around this loop stays the same. But we can have different types of spaces, which we're very familiar with, at least in concept. So without the same initial and final. And an example of this is two-dimensional spherical space. A great example of two-dimensional spherical space is actually the Earth. Okay, so we have a sphere, but then let's say that we have, for just the sake of argument, I'm going to draw a pretty simple loop. I'm going to draw one that goes down like this, oh, like this, and then like this. So the starting point and final point are the same. This is indeed a loop. But if I transport along this right here, but if I have the vector and I start here, then it's going to go like this, and it's going to be a little here. I just need to make sure that I'm drawing this correctly. Yes, okay, so it's going to look more or less the same coming down. Come on. Turn a little bit. And it's going to be like this. And then as it's transported along here, it's going to be like that. Eh, Okay, forgive me for taking a while with this. It's just trying to make sure that I get the angles and everything right. Okay, yes, so it's going to start like this, continue, keep going. And then when it's back at its initial point, it looks more like this. So I didn't get it like perfect, but the idea is that there's curvature in the space. And so when I go around this loop, I end up with different, we call this one the initial and this one the final. So this means that the field, so therefore the field can be curved. This connection can be curved. Let's look at an example so let's consider uh, discrete two-dimensional space. Let's consider discrete two-dimensional space-time. We will start with the field value at some point n. So this is a field value at n. And use the connection AJ to transport the field value into the neighboring point coordinate system. Neighboring points, multiple points, coordinate systems. So recall that phi of n minus the connection lives in the coordinate system at the point n plus ej. So we first need to recall this. When you have a point at n, then if you consider the connection in the jth direction and you subtract that from it, then the resulting value lives in the coordinate system at n plus e sub j. So suppose we go in the following loop. Suppose we take the following loop. So n goes to n plus e1, which goes to n plus e1 plus e2, which goes to n plus e2, which then returns to n. And this is the same as if we have 1 point, 2 point, 3 points, 4 points, going from point n to n plus e1, n plus e1 plus e2, and then n plus e2. So this is the same as going from here to here to here to here. That's the loop that is formed. Well, n sees phi of n, which implies n plus e1 sees phi of n minus a1 n, right? Because this lives in the coordinate system at the other point. So if we're at the other point, then we have to consider this to see the same value. So this value changes in the coordinate system at this point by this amount. And you can just continue with this. So this implies that when you have both points, you see, or it sees phi of n minus a1, but then you went in the other direction. So you went in the second direction from the point E1, n plus E1. So you get this as the value that is seen by this. So now if we then want to go, we're currently at this point, we want to go to this point. Well, this is just the same, or going from here to here is just negative of going from here to here. So instead of subtracting, we're going to add the next one. So n plus E1 plus, or so like going here, when you add onto the point here, you have to subtract. But here we're subtracting E2, so we have to add. So this point sees, or actually, sorry, this we're subtracting E1, so it'd be E2. It sees phi of n minus A1 minus A2. But then again, because we subtract E1 here, so we have to add a connection, and that connection ends up being in the A1 direction, E2, right? Because this being positive indicates that we're going from here to here. And then likewise, from here to here, this is also going to be a positive value. So you get negative connection, positive connection, positive connection. So then the n finally sees this whole value plus A2, then n. Let's bring this up here. This final value is written phi prime of n. Now, if if the field A mu is flat, so not curved, then phi n minus phi prime n is equal to 0. And then if it is curved, then the difference between these two values is not equal to 0. It's a non-zero value, which makes sense because that's what we had here. Here, they are the same. So if you consider the difference between the two, they'd be 0 because you'd be subtracting a vector from itself. Whereas here, you have two separate vectors, so subtracting them would actually result in a new vector. So that makes sense. This is a way for us to account for this. First, let's actually expand out this difference. So we have phi of n, of course, then minus. Well, we just have to subtract this from it. First value is phi of n. So now you can see that the difference between them actually doesn't matter what point you're considering, because the connections are going to be the only bits of information left over. So we get minus a negative, so we get plus a1 n, then minus a negative a2 n plus E1, and then minus a positive, so A1 n at E2, then minus a positive, so A2 n. And then we can we can cancel out this and then rearrange these terms, and we get A2 at E1 minus A2 at n minus A1 n at E2, and then minus A1 at n. And this is labeled F12 for this point. And this right here, this is actually a measurement of curvature in two-dimensional or in discrete 2D spacetime. So that we can consider general points and general directions in two-dimensional discrete spacetime. This would look like C j k, some point n is equal to a k n plus e sub j minus a k and minus a sub j n plus e sub k minus a sub j at n. And in continuous, one plus three-dimensional spacetime, well, before I write it out, let's motivate kind of what this is doing physically. Well, you're taking a point, you're taking the connections value. This right here takes the connections value at this point. And then it looks over here, or first what it does is it takes this point here, and then it looks at what the value of the connection is here and what the value is here, and then it subtracts them. Or here on. So my bad. Ignore what I just said. I'm going to say it in better words. So this is the connection at this point, and this is the connection at this point. So it shows this direction, and it's subtracting them, and then subtracting essentially the same thing on this side, and it's seeing if there's a difference. And if there's a difference, then there's curvature. So if you were to go to continuous spacetime, what you're doing is you're going to have an infinite amount of points and make everything continuous. And so these changes between points would be infinitesimal. So really what you're doing is you're looking at the infinitesimal changes in a loop about a point that's infinitely small. So if you're guessing that derivatives are involved, then you have guessed right. So if you're at a point x mu, then it ends up being d mu a nu minus d nu a mu x mu. And this probably looks familiar to you it probably looks like curl, and that's because that's exactly what it is. This is the vector derivative of curl. So it turns out that curl is what describes the curvature of a space. So if A is curved, then the curl of A will tell you how curved it is. The existence of curvature directly affects the physics of a system. It does so by providing a non-trivial background structure, and this non-trivial background structure is called the gauge field. So we call this we call this the gauge field. And these become very important. For example, if you have some scalar field f, then you have some other field, or I said f. This is phi. Then you have some other field, and these are related to each other by this gauge field. And likewise, there is something like this in. There will be something like this for spinors, but the idea is that if you have a scalar field, then you get the dynamics of a field through a connection. And for example, this would an example that we know is this would be electric potential, uh, and then this would be the or electromagnetic for potential, and this would be the electromagnetic field.